The same principle I told you about, we start with expensive metals, yet they're more sustainable than the state of the art. Then we move to less expensive metals like copper and iron. We apply that also for photovoltaic materials. So organic photovoltaics, typically you need to overlap with sunlight. So this AM0 here, the one that you see in pink color, shows you the sunlight. So a little bit chemistry and physics here. So the electromagnetic region from 400 to 800, that is the visible region. So this is where the red color starts. This is what, where the blue color starts. This is what the red color ends. So the peak of the solar radiation is about in the green region at about 550 nanometer, and there are organic material that you see here. This polymer P3HT overlaps very well with that. So we can make devices. Other people make devices with such polymers, but as you can see, there's poor overlap at shorter wavelength in the visible and at longer wavelength in the visible as well. They can try other materials that improve the overlap at the longer wavelengths, but there is a greater vacancy, greater vacancy at the shorter wavelengths. Our favorite materials are these beautiful black absorbers. So this is the other black gold, or the other, besides petroleum, right? So this type of material here absorbs the entire visible light from the blue to the red, and even penetrates into the near infrared. Your eye can't see, but as you can see here, it tells of the sunlight, tells of there's actually more than 50% besides at longer wavelength than 800 nanometers. It goes beyond the visible region to the near IR, and our material here overlaps with it extremely well. So we can catch the sun, we can catch some rays, like I learned in Maine many years ago, right? So we can harvest this sunlight in its entirety by using these beautiful crystals, and then we can actually measure the device measurements in the clean room to confirm that we actually can produce electrical current. So as you can see here, the current versus voltage. When you drive the device, in absence of light, there isn't much current going on, right? But if you irradiate it with UV light, visible light, near-infrared light, a lot of current can be produced, and it is constant because it absorbs everything uniformly. Then we look for nature to inspire our design for cheaper materials. So for example, organic materials have, most of them have white color, but some of them have visible color. So if you look for ethylene, for carrots, for example, the building block for carrots is what chemists call a carbon-carbon double bond, right? So this carbon-carbon double bond, the major constituent of an oligomer like beta-carotene that's responsible for the orange color in carrots, has absorption in the far UV. You can't see it. It's very far from the visible region that I told you at about 400 nanometer. So as you increase the number of these ethylene units next to each other, if you have 11 right next to each other, that's what produces the orange color in beta-carotene to give this color. If you have 13, that gives you the red. And the most beautiful color in solar is what? Black, like in eggplant. So you can produce that. So what is our trick here? So that is the problem with those. OK, sounds great. You can make solar cells. Actually, I think my colleague, Dr. D'Souza, he can make dye-sensitized solar cell based on blackberry and other berry juices in his lab. The problem with them, they're not very stable. So if you add a metal to these carbon-carbon double bonds or carbon-nitrogen double bonds, okay, you add a great amount of stability for the material, so you can shine intense light on it, so the device will not degrade in seconds or minutes. It can last for years and thousands of hours, okay? So that is our approach. So we look for these organic ligands. Ligands means the organic molecules that bond metals with one another. So if you increase the conjugation from one to the other, if you increase the number of double bonds here from the left to the right, okay, you can render these visible color if you conjugate them with a metal center like copper infinitely. Okay, so these are so-called coordination polymers, means that these double bonds can be connected with one another 1 dimension, 2 dimension, 3 dimension, right? Infinitely, not only 11 or 13, they can go infinity. When you do that, you can produce black color with this type of organic ligand. That's what we proved. And I'm very proud that this work actually was the work of my graduate student, Roa Al-Mutawa, who started with my better half, Dr. Munara Omary from TWU, as her master's degree. And then she continued on with her work. We recruited her, and we filed a common patent together where she is expanding the scope of these materials to use them in organic photovoltaic devices. OK, so that is the second app. The third app is energy storage. So we talked about energy-saving lighting, energy harvesting solar cells. And now we need to store energy so we can use the energy from sunlight in the daytime and use it in the nighttime. So that is one means for energy storage. Another means of energy storage, what I told you earlier, okay, these porous materials, they can store high energy molecules like natural gas, organic materials, hydrocarbons, okay? And basically, you can store materials from the gas phase, condense it in the solid state phase, and when you do that, you can basically empty the content of this giant tanker in this little cylinder that can fit in the trunk of your compact car, or even Volkswagen Beetle, if you wish. So this is how we do that. This is this material that we discovered serendipitously. In addition to the energy storage that we can utilize natural gas, which pumps about 50% less CO2 to the atmosphere, we can use them simultaneously for environmental applications. One unique properties for these so-called super hydrophobic means they really, really, really hate water. Okay? They don't absorb any water, much better than the hate for other common adsorbents like zeolite and activated carbon. Activated carbon is the stuff that you get if you burn biomass to death. Basically, if you have any organic material, any knaf trees, my colleague Sheldon Shee from MEE, Mechanical and Energy Engineering, he's expert in making ultra-porous carbon-based materials. So these actually supposed to hate water, but as you can see here, they resist humidity only to about 40%. So a lot of the applications for porous materials and energy storage and others, they occur at much higher energy, moisture levels, and some of them in liquid water. One common problem that actually we made some national headlines on is the oil spill. When we discovered these types of materials, we found that oil molecules can penetrate and be stored in the pores of these type of Flourous metal organic materials. So oil is welcome to these pores, but water is not. We discovered this in 2011. At the time, it was still fresh, the Gulf of Mexico Deepwater Horizon oil spill. So C&E News picked up our article that we published in the Journal of the American Chemical Society and wrote a highlight article about using our materials for potentially safe disposal or safe containment of oil spill, or at least, you know, the water that remains after you skim off the major spill, the water that remains would be a lot safer to even drinking or other uses.